Higher order derivatives. Second derivatives are derivatives of derivatives. We denote these by f double prime, or d2f dx squared, or d by dx of df dx, or y double prime. For example, we might want to find the second derivative of f of x equals 3x to the 5 plus 2x plus 1. The first derivative is easy to find. It's 15x to the 4 plus 2. Differentiating again, we get 60x cubed. According to the laws of physics, the height of an object near the surface of the Earth falling in a vacuum from an initial rest position s0 feet above the ground under the influence of gravity is approximately s of t equals s0 minus 16 t squared feet, where t is in seconds. Find the acceleration. Well, the first derivative of the height is going to be the velocity. The second derivative is going to be the acceleration. So v of t is equal to s prime of t, which we can see as negative 32 t feet per second. A of t is the derivative of v of t, or the second derivative of s of t, which is negative 32 feet per second squared. 32 feet per second squared is in fact the acceleration due to gravity. Concavity. We say that a graph of f is concave up and the graph of g in the diagram is concave down. A curve is concave up if its slope is increasing, in which case the second derivative is positive. A curve is concave down if its slope is decreasing, in which case the second derivative will be negative. A point in the domain of f where the graph of f changes concavity from concave up to concave down, or vice versa, is called an inflection point. Concave up graphs lie above all of their tangent lines. Graphs that are concave down lie below their tangent lines. And that's what we use as our definition. If the graph of f lies above all of its tangents on an interval I, then it's called concave upward on I. If the graph of f lies below all of its tangents on I, it's called concave downward on I. In this graph, we can see between A and B, we're going to be concave down. We have an inflection point at B, where we then switch to concave up between B and C. At C, we have another inflection point, and we're concave down between C and D. Again, between D and E, we're concave up again between E and P, and concave down between P and Q. If f double prime is greater than 0 for all x on some interval I, then the graph of f is concave upward on I. If f double prime of x is less than 0 for all x on that interval I, then the graph of f is concave downward on I. What's the concavity of y equals x to the 4 minus 4x cubed? In order to discuss this, we want to take a couple of derivatives. The second derivative of y here is going to be 12x squared minus 24x. Y double prime is equal to 0, then when x is equal to 0 and 2. When x is less than 0, we can see that y double prime is greater than 0. So y is concave up on negative infinity to 0. When x is between 0 and 2, y double prime is less than 0. So y is concave down on 0, 2. Finally, when x is greater than 2, y double prime is greater than 0. So y is concave up on the interval 2 to infinity. Figure 11 shows the graph of y equals x to the 4 minus 4x cubed. We can see we've got inflection points at 0 and 2. We're concave up from negative infinity to 0. We're concave down on 0 to 2, and we're concave up again from 2 to infinity. A curve is concave up if its slope is increasing, in which case the second derivative is positive. A curve is still concave down if the slope is decreasing, in which case the second derivative is negative. So a point P on a curve y equals f of x is called an inflection point if f is continuous there, and the curve changes from concave upward to concave downward, or from concave downward to concave upward at P. The second derivative test tells us that if f double prime is continuous near C, and if f prime of C equals 0, and f double prime of C is greater than 0, then f has a local minimum at C. If f prime of C is equal to 0, and f double prime of C is less than 0, then f has a local maximum at C. You can see that in the graph here. If we can compute first and second derivatives, there's no reason why we can't compute third, fourth, fifth, nth derivatives. In terms of notation, we talk about f prime, f double prime, f triple prime, etc. Or df dx, d2f dx squared, d3f dx cubed, etc. Some notation is in the left margin. We might be interested in finding the nth derivative for a function. For example, y equals x times e to the x. Well, our first derivative, by the product rule, is e to the x plus x e to the x. Our second derivative is just the derivative of y prime. In this case, e to the x plus e to the x plus x e to the x, or 2 e to the x plus x e to the x. Third derivative, we end up with 2 e to the x plus e to the x plus x e to the x, or simplified, 3 e to the x plus x e to the x. We start to see a pattern. And so after n derivatives, we can see that the nth derivative of y is going to be n e to the x plus x e to the x.